Hello, in this video we are finishing our discussion of convolution by working through one more exercise. We're solving another initial value problem with a general right-hand side, but notice, similar to the previous exercise in the previous video, but notice that our initial conditions on our left-hand side are a little bit different. So again, we're going to assume that the Laplace transform of that general function does exist so that we can use the method of Laplace transforms. So the first thing that we are going to do is we're going to take the Laplace transform of both sides. On the right-hand side, that will just turn into a capital G of S, and on the left-hand side, we are going to use the linearity of the Laplace transform and also some other properties to get what we have here, s squared y of s minus sy of 0 minus y prime of 0 plus 4y of s is equal to g of s. Then doing some algebra, we will combine our like terms, move our non-y of s terms to the right, and solve for y of s. So we get 3s minus 1 over s squared plus 4 and g of s over s squared plus 4. So clearly this last term we're going to have to use convolution on since we don't know what capital G of s is. But this first term, we can just use some normal techniques. We can split that up into a couple different terms, 3 times s over s squared plus 4 minus 1 over s squared plus 4. And notice that s over s squared plus 4 is the cosine of 2t, or it's the Laplace transform of the cosine of 2t, and 1 over s squared plus 4 is the, well, almost the Laplace transform of the sine of 2t. We do have to modify it a little, which you will see in just a minute. So for this last term, we're going to have to apply convolution. We need to identify what our different functions are. Our first function, we're going to say is this 1 over s squared plus 4. And notice this is the same as what we had there, so this will help us later on as well. Like I said, this is almost the Laplace transform of the sine of 2t, but not exactly, because we need a 2 in the numerator. So if we put a 2 in the numerator, then we need to also divide by a 2 so that we're not actually changing it any. And then this gives us that f of t, which is the inverse Laplace transform of this, is 1/2 sine of 2t. And for our other function involved in the convolution, well, g of s is just the Laplace transform of g of t. So g of t is just the inverse Laplace transform of capital G of s, and we can't simplify it any more than that. So then, convolution theorem combined with what we have up here says that y of t is going to be the inverse Laplace transform of all of this. So that's 3 times the cosine of 2t. And then here we know is a 1/2 and the sine of 2t, so we get minus 1/2 sine of 2t. And then the convolution theorem says that we integrate from 0 to t. We have the sine of 2 times t minus v times g of v, or because of properties of convolution, we can reverse the order. We could also write it as the integral from 0 to t of g of t minus v times the sine of 2v. And depending on what exactly that function g of t looks like, we may want to do this order, or we may want to do that order, whichever one ends up being simpler in the case when we have a specific g of t function. So this is another solution similar to the previous exercise where we have a general solution for any right-hand side function. And this is a sort of process that we can do now with any linear higher order differential equation with constant coefficients on the right-hand side. And we can also do a little bit with some non-constant coefficients with Laplace transforms as well. So we get a lot more versatility with the method of Laplace transforms than we do with some of the other methods that we have seen in differential equations. And that does wrap up our discussion of convolution.